So the vertex view, then, continuing from the last interval, is taken for the transverse plane misalignment of C1. So what we do here then is we mark the transverse foramina on either side, and that establishes the plane of the atlas in the transverse plane. But to check, because the transverse processes, foramina, are not always symmetrical, we always also mark the anterior and the posterior aspects of the lateral masses. And you can even, bisect those and come up with a line that represents that. But in a case like this, where this is so symmetrically aligned, either one of these, any one of these three lines would represent the rotational component of C1 in the transverse plane. So there should be agreement between these points. And if not, then one needs to justify, but not all transverse foramina are symmetrical. So, and we're not measuring that so much as we are what the atlas is doing. So the lateral masses is a more accurate way to measure the rotational component. So the next thing that we do is we look for the spinous process center. And so earlier when we were doing the nasium, we looked at what the spinous process was doing in the frontal projection, but it's actually a rotational or transverse plane component. So here then, this looks at that specifically. So the base of the dens is bisected and a vertical line established inferior to the dens. So you select the points on either side of the base of the dens, and then the program will drop a vertical from that point. The lamina-pedicle junction is the next point that we look at, and that's when you look at anatomically. So the vertebral end plate of C2 is represented by the base of this isosceles triangle, and then where you can see these loops come up and around upside down U's here and here, those are the lamina-pedicle junctions and the first true intervertebral foramen with the C3 nerve root coming out at that point. And so then we construct an isosceles triangle. And the point of that triangle then is measured, its rotational component, off of midline of the dens. And so this would indicate that the C2 spinous process or spinous process center has moved to the right of midline a little bit. So that would indicate, in this case, that with right laterality, as we did on the nasium, that this would represent an inferior spinous. So the next line that we select is the vertex skull line. The vertex skull line is drawn as a vertical line that should bisect the skull, the cervical spine, and the sphenoid. And so this line is set up initially as a vertical line, but in fact it can be altered, rotated off of vertical in order to accommodate for example, an imperfectly taken vertex. But in this case, you can see that it bisects the sphenoid, and this is a proper line. So this is the vertex skull line that then establishes the midpoint of the cranium. It's similar to the central skull line. As a matter of fact, in this program, the function that selects the vertex skull line is actually just a cephalometer that once again can be sized to analyze the entire skull, or it can be used in the traditional sense to bisect the midline. So once we've established these vertex skull line and the line through the transverse foramina, we measure the angle. And so in this case, since once again we're looking at right laterality, we're looking at the right transverse process. And in this case, visually, it assesses as an anterior on the right. If this were left laterality, it would then be a posterior on the left. So in the program, then, it allows you to select either a left or a right laterality. And once you select that, that would go from left posterior to right anterior. So that's the designation. And so in this case, it measures 1.91 degrees of anterior rotation on the right. So now that concludes the analysis, but not the calculations. So in order to come up with the height vector, which is the vector off of the nasium, by the way, this rotation, C1 rotation vector is the rotation vector. So that measurement is the rotation vector, whereas in this case, in order to get the height vector off the nasium, we have to sum four values. We have a plane line measurement, we have a head tilt measurement, we have a condylar axial relationship measurement, and an angles measurement. So these are the four pieces of information that need to be, well, we've already measured them, but they need to be calculated in order to come up with the height vector. So the height vector, or HV, is the sum of these four factors culled from the nasium image. Depending on the numbers and the anatomic features, the sum can be a positive or negative number. And 0 is at the contact point in terms of doing the calculation for this, is the contact point of the C1 transverse process. So for example, in a basic type 1, the plane line value is always a positive number. In a basic type 1, for example, head tilt is always a 0 factor. The condylar axial ratio is a factor that is always greater than 0. And in a basic type 1, an angles measurement will be always equal to or greater than 0. So you can see that for a basic type 1, the height vector will come out as a positive value. In a basic type 2, it's a little bit different because typically, and now we're not going to talk about atypical cases, but typically the plane line can be around horizontal, so not too high, not too low. Head tilt in a typical type 2 will be a negative value. The C over A is always greater than or equal to 0, and angles will always be less than or equal to 0. So you can see for a basic type 2, the potential is there given that the condylar axial ratio is not a very high value, that you can come up with a low height vector, so a negative value. Basic type 3, basically there's no angles measurement because there's no lower angle. And in a basic type 4, plane line, once again, in a typical case would be a positive value, height vector will be a negative value, condylar axial circle, will, as in all cases, will be greater than or equal to 0, and angles will be, like in a type 1, greater than or equal to 0. So in a type 4, 3 out of 4 factors will be 0 or higher, and head tilt will be a negative value. So now let's look at the specifics. So first we look at plane line. So these are the rules, and I've done this, for example, this formula is like haiku. I try to condense it as much as possible to make it as concise as can be. So when the APL is above horizontal on the side of laterality, the formula calculates as, for each 3/16 of high APL, add 1 inch to the height vector. Then it breaks down further that for each additional 1/16 of an inch, add 1/4 of an inch to the height vector, and for each additional 2/16 of an inch, add 3/4. And this, is kind of a messy formula, but that's how it was in the analog world, and this is how this was developed. Now, when the APL is below horizontal on the side of laterality, the calculation is the same, except the formula subtracts the same values. So which it would read, for each 3/16 of low plane line, subtract 1 inch from the height vector. And then for each additional 16th, subtract 1/4, and for each additional 2/16, subtract 3/4. So that then indicates that as the plane line goes up on the side of laterality, let's say on the right side, that the higher the plane line, the higher the value for the plane line reduction component. And to some degree, that works on a low plane line as well. So now, and this is once again a newer development, we now look at head tilt as a calculation. So in cases where the central skull line is tilted into the same frontal plane as laterality, in other words, that if you have right laterality and right head tilt, like we had in the case that we did, Nuka calculates this as follows. For each degree of central skull line or CSL tilt, you subtract 1/2 inch from the height vector. So that's straightforward. However, in cases where the CSL is tilted more than the value of laterality, subtract only the degrees of laterality and not the full amount of CSL tilt. So for example, over here, if we had a 0 plane line and we ended up with um, a head tilt of 3 degrees, according to this formula, you would subtract 1.5 inches from the height vector. But let's say that we had a low plane line that measured roughly, 3/16 low, and we had a right head tilt of 6 degrees, but only 3 degrees of laterality. So in that case, you would still only subtract the amount of head tilt that represents laterality. In other words, it would still only be a 3-degree calculation, which would be subtracting 1.5 inches from that value. Gotta hope that's clear. All right, so moving on then, the condylar axial circle. This is the ratio of the condylar to axial circles or arc segments, and it can be expressed as a formula, which is in parentheses a minus c, so you do that first, divided by 2. That's probably my favorite part because it's a really straightforward part of the formula. In the event that the arc measurements are fractional, in other words, like if you had a condylar 3.5, you would round down to the next whole number. So 3.5 becomes a 3. And for the axial circle, for example, you had 4.5, you would round up to the next whole number, so that would become a value of a 5. And then finally, we have the angles measurement. So NUCA has 4 basic types of misalignment categories. So the angles calculation only applies to 3 of the basic types. Why? Because basic type 3 has no lower angle, no cervical line, so there's no calculation for that. So the formula is like this. In basic types 1 and 4, when the central skull line is greater than laterality, in other words, when the cervical line has a higher acute angle than laterality, you add a 1/4 inch for each degree of difference. So if you have an upper angle of 3 and a lower angle of 6, that's a differential of 3, so you would add 3/4 of an inch to the height vector. In a basic type 2, what you have then is when the cervical line is greater than laterality, you subtract a 1/4 inch for each degree of difference. So it's basically the opposite of a basic type 1. So when the lower neck or the cervical line is misaligned more than laterality, rather than adding to the value, you subtract.